Coming to three-phase transformers, this is the arrangement of three-phase transformer. These are primary windings and these are secondary windings. Number of turns on the primary is less compared to number of turns on the secondary. That means this is a step-up transformer. These are the voltage waveforms on the primary. These are the voltage waveforms on the secondary. On each limb, we are having both LV winding and HV winding. This is for R phase, this is for Y phase, and this is for P phase. In case of single phase transformers, we had seen primary voltage, flux in the transformer core, no load current, working component, and magnetizing component, primary side current, primary side back EMF, primary winding, resistance, reactance, iron losses of transformer, equivalent circuit of transformer, and vector diagrams, including secondary side back EMF, secondary side current, terminal voltage, secondary windings resistance, and reactance. All these things we had seen for single phase transformer. In case of three phase transformers, all these quantities will be repeated for R phase, Y phase, and B phase. So we will be having three quantities each, and all these things will be at 120 degrees apart. So this was the vector diagram we had seen for single phase transformers. In this vector diagram, we are considering this primary side terminal voltage as the reference. This is the primary side back EMF, voltage drop due to resistive branch, voltage drop due to reactive branch, and this is total drop with reference to impedance, primary side current, which is vector sum of no load current and secondary reference current on the primary. This is the vector diagram with reference to type of load. Here we have considered only resistive load. So terminal voltage V2, secondary load current I2, secondary side voltage drop with reference to resistance, and this is with reference to reactance, and this is the total impedance, and this is secondary side back EMF. This is the vector diagram with reference to resistive load. The same network can be repeated for inductive loads and capacitive loads. So this is for only single phase transformer. But in case of three phase transformers, we will be having vector diagram like this, which is very complex. This is the vector diagram for R phase winding, and this is the vector diagram for Y phase, and this is P phase. So we are taking primary side voltages as reference. This will be VR, VY, and VP. So these are the voltages which are exactly 120 degrees apart. Three single phase transformers can also be considered as a three phase transformer. This can be for R phase, Y phase, and B phase. Coming to turns ratio of windings 1:n. If n equals to 1, then it is 1:1 transformer. If n is lesser than 1, then this is a step down transformer. If n is greater than 1, then this is a step up transformer. 1:1 means this is for only electrical isolation. If we see the configurations of windings on primary side and secondary side, for distribution networks, we can go for star connection. Delta connections we can use mostly in transmission networks. Delta by star or star by delta, mostly we will be using these connections in industrial practice. So any of the connection can be used for step up or step down. But star connection on secondary mainly adds advantage so that we can have neutral conductor or ground conductor. It will be helpful for distribution network. And VL equals to root 3 V phase or V phase equals to VL by root 3. That means for phase windings we can have low rated insulations. This is total representation of three phase transformer. Primary is delta connected, secondary is star connected, and size of the circle is large. That means this is a step up transformer. Primary side 3 lines indicated, secondary side 3 lines indicated. This is completely 3-phase transformer. We can indicate an arrow also. That means unload tap changer. Wherever neutral is provided, that connection we can consider as star connection. Transformation ratio in case of either 3-phase transformer or single phase transformer, the transformation ratio will be same. V2 by V1 equals to N2 by N1 equals to I1 by I2. If we take 3-phase connections or 3-phase transformers, then root 3 term will added to this equation, but this root 3 term will get cancelled either by voltage or either by current. This factor will get cancelled. Finally, we will be having only one transformation ratio, that is V2 by V1, N2 by N1, I1 by I2. This is same for both single phase transformer or 3-phase transformer. Voltage ratio and current ratio, these two must be taken at the same time. So K V2 by V1 equals to I1 by I2. In case of single phase transformer, the rating of transformer in MVA equal to V1 I1, that is also equal to V2 I2. In case of 3-phase transformer, MVA rating equals to root 3 into V1 I1, that is also equal to root 3 into V2 I2. If we take the ratio either by current or voltage, then this root 3 term will get cancelled. So the transformation ratio K will be equal to V2 by V1 equals to N2 by N1 equals to I1 by I2. All the parameters such as currents, voltages, MMF, turn ratio, all other parameters we can take phase values, that too in RMS. Copper losses, iron losses, this has to be multiplied by 3 for 3-phase transformer. In case 3-phase transformer, the power will be 3 times of phase voltage, phase current and phase angle.